Dan, als het goed is, moet hij werken. Dus dan gaan we even naar YouTube toe. Hopla.
Ik zou Mac met 2 schermen hebben.
Dan moet ik naar mezelf gaan. En dan moet ik naar mijn channel gaan. YouTube Studio. En dan... Oké, dat is goed. Video's. Live. Nou, als het goed is dit livestream. Ja, hij zegt dat hij live is nu. En dan kunnen we ook nog apart bekijken. Hier, gewoon bang, dan zien we hem. Ja, hij werkt nog goed. Zie je?
En als je nu wat tekeningen of wat...
Ja, zo. Oh ja, mijn tablet. Ik ga mijn tablet naar boven toveren.
Ja, wat niet zo anders, iets anders op staat.
Nee, dit. Ja. Oh, dus ik weet niet. Dan moet ik eigenlijk een nieuw ding maken. Nou, je ziet hij doet het. Dus het werkt allemaal nog wel, ondanks de...
wijziging.
Ja, anders wordt het denk ik wel complex, want dan zouden die jongens van netwerk moeten kijken of ze erop zien op het netwerk, maar dat wordt wel een hele uitdaging.
Ja, wat ik ook goed zou vinden, als ik via een kabeltje hier naartoe kan. Maar ik heb me suf gezocht, ik kon nergens een oplossing vinden waarbij je je iPad met een kabel aan je MacBook maakt en dan als zoveelste scherm. Heb ik niet kunnen vinden gewoon. Ik heb het ook wel eens uitgezet gewoon, lang geleden.
Is dat er dan niet gewoon een Lightning naar USB-C die dat soort informatie verstuurt?
Ik heb het niet gevonden. Ik heb wel dingen, je kan wel naar buiten, je kan dit scherm, je kan hier een scherm aan connecten en zo. Maar via deze informatie naar deze en hier een scherm laten zien, dit was de enige.
Dat zal toch wel de enige oplossing zijn.
Ja, hè? Ik dacht ook van
ik zal wel even googlen.
Maar als jij nog iets kan vinden, dat zou natuurlijk helemaal mooi zijn. Want als het een kabelverbinding is, ja, dat is veel zekerder dan hier wat maar door de lucht zit te friemelen.
Ja.
Dat zou ik heel erg mee geholpen.
Ja, wat ik zeg, anders wordt het wel een hele uitdaging om het via jongens van netwerk te laten uitzoeken. Wat de drops zullen zijn in het netwerk om daar zicht te krijgen.
Ja.
Ik geloof niet dat het resultaat gaat opleveren.
Nee, dat denk ik ook. Maar ik denk, omdat ineens hier weer, omdat in deze zaal begon ik natuurlijk naar de zaal eerst te wijzen en zo. Ja, ik weet het ook niet.
Nou ja, het is sowieso een stuk drukker altijd met netwerk hier in de omgeving ook. Als ik bedoel, zo'n collegezaal leeglopen, lopen er 100 man met een telefoon en een laptop rond.
Ja.
Dat zijn allemaal wifi-punten.
Ja.
Nee, is er dus wel een
kabel?
On your app, iPad, open the Duet app, maybe you moet downloaden and plug it into your Mac. Nou, ik ga wel even...
Ik moet colleges zo voor gaan bijdoen.
Is goed.
Het verhaal is duidelijk.
Ja.
Bedankt voor je inzet.
Okay.
Ja, en Arthur, kijk er naar uit.
Yes.
Okay,
dank je. Wat hebben we? Lecture 3, hè? 3, ja. Nee, ik praat hardop. Let maar niet op mij. kruk.
Screwdriver solution books.
Hoi. Nou, ja. Bril.
Kijk, gaan we daar.
Okay, welcome to the third lecture on multibody dynamics. The dropout of the screen thing, connection, Wi-Fi, whatever, it's under study. We tried some things. I hope it's resolved, but don't be disappointed if it drops out a couple of times again, these two lectures. We're working on that. Okay, today's topic is a continuation of a systematic approach. And we're going to look at, okay, now we have a multi-body dynamic system. We want to add passive and active elements and things like springs and dampers and motors, and that makes then the whole multi-body dynamic system complete. And we're also going to have a brief look at impact equations, because that's an idealization of a thing which happens, and it happens usually quickly, so you don't want to follow that in time, so you want to set up special equations for that. Okay, that having said, where should I start? Right, I see all kind of mouthing going on, but I guess it's this Kahoot, right? Okay, Kahoot, where art thou? Here, number 3. Oh, I should do this for you, right? Classic. Sound. Okay, while everybody is now logging in, a very short story. Monday I was in Utrecht. So what? I was at the University of Utrecht and I was giving a guest lecture in a lecture on geoscience, on physics. I was giving a guest lecture on bicycle dynamics and control. And they were freshmen, first year bachelor students. And I used Kahoot. And it was fun, because it really showed like, oh yeah, I don't know everything about bicycle dynamics and control, apparently. It was a nice exercise. Okay, where are we? Oh, still not there. What did I do more? You're not interested, right? Not so very thrilling. But oh, tram line 22 was very nice. It cost a few bucks, but no, really. I mean, from the central station you get like in a jiffy you're at the university at Utrecht. Of course you can use your bike. I usually use my bike, but this time I just wanted to do the tram. And there's a special thing in the tram. The things to peep in and out are not in the tram, but they're outside. Like, is it a tram or is it a train or? Very strange, yeah. I'm used to peeping in and out in the tram. Are we already there? Okay. Yeah, this is about the number we have usually, right? 103 something. Okay, let's start the quiz. Yeah. Are you ready? 5 questions. And the first is about very recent news. Last Friday, a brilliant theoretical and physicist mathematician, aged 96, passed away, and his name is... Only 30 seconds. You know or you don't know? And this is, well, you have to follow the news, right? You have to know within science what is going on. Okay, for those 75 who have the correct answer, perfect, you know all the details. For those 15 plus 17 plus 12, which is a big number, what is it? 44, right? For those 44, let me. Why do I do this? Well, first of all, when you're at university, I expect you to follow the scientific news. You should be up to date. What is going on in scientific country? And Freeman Dyson, FRS, so Fellow of the Royal Society. Why is he so interesting? Well, first of all, he is like a multi-talent guy. He was good in number theory, in particle physics, in space exploration, in the theory of evolution. He looked into extraterrestrial life. Climate change was a topic for him, and nuclear disarmament, nuclear disarmament. 96, so he was also involved, of course, in Los Alamos with those guys. He was at Princeton. He got his master's from Cambridge and his PhD. He never got his PhD. He was what he said. I always stay a student. And how did that come? Well, when he graduated, he went to the US, and it was such a brilliant guy. I mean, he just didn't finish his PhD. He just was employed as a full professor at Princeton, and then he had a stint at Cornell, but then back to Princeton, and that was it. Remarkable guy. And why do I show this? Well, first of all, you have to follow the news, but there's also a connection with our research on bicycle dynamics and control, because I like to quote one of his many things he said in public, and one of his quotation is this. That's from 1998 in an interview with Stuart Brand for Wired. He says, "Even now, after we have been building them for 100 years, it's very difficult to understand just why a bicycle works. It's even difficult to formulate it as a mathematical problem." So that is, although it looks simple, the whole bicycle dynamics and control, it turns out to be not so simple. And even Freeman Dyson says so. Okay, we'll move on to the next question. So probably next week I also have some contemporary topic thing scientific in the news, so watch out, right? Is LL in the room? Eternal Fame? No. Okay, back to business, right? It looks like everybody knows the answer. Discuss with your neighbor, convince him, he's stupid, you are smart. Yeah. Okay, that wasn't so hard, right? Now for the 44 plus in the room, what is going on? Why is it not 1? Well, this is 1 degree of freedom, that's clear. But in this very special case, when both bars have the same length and it's in exactly the same position, there are actually 2 modes. This is 1 mode, and the other mode is that as 2 bodies together, they just go in circles. And that's exactly was also the topic of the last item in the homework assignment. Okay, we'll see. Anyway, next. Yeah. Oh, I don't know what that is. Yeah, this here you really should use pen and paper. You have 90 seconds. You have the constraint, and I like to ask, what is the interpretation of the Lagrange multiplier? And it doesn't take much, but just take the constraint, differentiate it, write down the the equilibrium equation and identify what the lambda is. Or guess an answer. You have enough time, you have even more than a minute. You now have a minute, so just scribble, calculate, differentiate, equate, hibernate, vibrate, contemplate, procrastinate. You can also rule out wrong answers and maybe the right answer pops up. That's also a strategy. Okay, for the, what is it, 40, oh, it's increasing. It's now 51, right? For the 51 wrong answers, let me just exemplify. If this is the constraint, then the Jacobian goes into the equilibrium equation, right? So all the force associated with Fi is the differential of this constraint with respect to I. So that's a 1. Yeah? If I differentiate this with respect to I get a 1. So Fi is lambda. If I differentiate with respect to x, I get minus a. So minus a times lambda is apparently fx. That's how it is. Yeah. Next. BVR in the room? Okay. Kinetic energy of a system. Complex system, number of bodies, all have a velocity, Vi, for I is 1 to whatever. There's a mass matrix, Mij. Then the kinetic energy is, and of course I used here the Einstein summation convention. Eh? So the blues in the room may question why the yellows in the room are also correct. You would expect, oh, it's this answer, right? The I and then the J collapse. And why is this also correct? Because Mij equals Mji. It's a symmetric matrix, right? Okie doke. Anonymous. Energy loss during impact. Yeah, that's a smart one. Very good. I like that. Somebody is picking up his book and looking it up, which is legitimate. I mean, if you have a hole in your knowledge, fill it. you could also look at the units, the dimensions. Are they correct? Is it energy, or would you say answer whatever can't be because it's not energy? And what's happened in the special case? Yes. Although I'm tempted to say that the blue ones are almost also a little bit correct, right? I mean, it's almost identical, but for the half. And yeah, it's a deep thing. Why is there a half? That's a deep question. I don't have the answer ready yet. Well, sort of, but why is there a half? The other ones, well, you can immediately throw them away because the units don't comply, right? I mean, velocity squared is not energy, and impact squared, which is mass times velocity, is also not energy. So, okay, though. The podium, yeah. Anonymous on the podium. Oh. Yeah. I get feedback, that's good. Save the result. Show feedback. Save the result. Right, download. Okay, yeah, that's covered now. What was the feedback? Thank you. That works. Leave. Live stream is still running, that's good. And then we go to this guy. Yeah. Okay, let's have it here. Okay, so for today I want to look at the multibody system where we again use a systematic approach, but I want to add some realistic things to it, like passive elements, and a passive element can, for instance, be like a spring. But we also have like active elements, like active element, and yeah, like a motor. I usually draw a rotary motor, but it could, and then you, of course, you have a voltage here. But you could also think of a linear motor, something like that, the cylinder where you put in pressure or fluid or. Now let's focus first. Let's take this as an example, and I want to add a spring to my multibody dynamic system, and let's do it simple. So we begin with our first body, which is connected to the ground, right? This is our first body, and then of course the rest of the system. But for now, let's forget about that. Let's focus on adding a body, and I'm gonna take a support here, so I'm going to add a spring connected to this body, and I'm going to connect it somewhere on the body, not necessarily at the center of mass, of course. So there's a spring here connected in this point. We need dimensions, of course, for that. Oh no, we need the coordinate system. Oops, okay. So these are the angles. This is body 1, right? we need to know where this position is, this position E, and I call this D. Then I decided to mount it at L over 2, where the whole distance of this guy is L. And where do I mount the spring? On the body, on 2/3 of the length. So 2/3 of the length L. Then of course the spring has some properties, and let's assume it's like a linear spring, right? So if you have an elongation, then the force we get is just this line, and the law which goes by that is F is K times delta L. We called that the Hookean law because Hooke was among the first who formulated that law. So we say it has a linear stiffness, and it has, because we look at the elongation, it has some unstretched length, which we usually call L0. So that's the length of the spring when there are no forces. You buy a spring and you put it on the table. Sometimes it has a little bit pretension in compression. Yeah, but let's assume that it hasn't got that, and it's just the initial. And I take for now, to make life simple, just the length L. So that's like we don't have too much parameters. Meaning, if we talk about this spring, then the delta L is the length which is the current length LC minus C minus the initial length L0. So that having said, and then the spring force in our case here is of course Fs is K times delta L. And what is the length, the current length? Well, that's the distance of course between these 2 points, right? And so you could say that is the norm of the position of, what did I do? E minus D or D minus E, it doesn't matter. D minus the position of E, and the norm of that. That is the current length of the thing. It looks a lot like a 0, so I better fix that. Oh. Okay, so this is current length. Okay. And now the big thing is, of course, we have to put this passive element into our equation of motion. So we have mass times acceleration, we have Jacobian times Lagrange multipliers, and then on the right-hand side we have applied forces. And actually this is like an applied force. But we have a constitutive relation for that, a law, and you calculate it depending on the position. But whatever it is, if you know the configuration, you know, oh, this is the applied force. You could, of course, go to the trouble of, again, cutting this loose and adding a force and components and transferring it to the center of mass, and then you know the applied force. However, we have our systematic approach, right? And maybe with our magical cooking pot that you can get automatically all your stuff in the equation. So let's see how that works in the systematic approach. So systematic approach. Where did we start with the systematic approach? Which concept did we use? Virtual power, yes. So it's really like a student at work, right? Virtual power. Nah, you do good work. It's not like a student. Maybe it's like me. Okay, and what was the virtual power? Then we have to actually be specific. The virtual power of the applied forces and the inertia forces. Very long sentence, which I'm not going to write down. But in our case, it's this delta P. So we have the applied forces, Fi. We have plus the inertia forces, so plus the inertia forces. Yep. Times the virtual velocities. And remember, this delta has nothing to do with differentiation. It's just some symbol to say it's virtual. You could also use an index or whatever. And that should be 0. Yeah. For which? Well, for all these virtual velocities, which are part of the constraints, which fulfill these constraints. That was our thing. Is something happening? I still have a vision. What is this? Now it's gone, right? What happened before it disappeared? You already saw something, right? Okay. Okay. Sorry for that. Apple TV. Go to this guy, to this guy. Show the iPad. Have it. Okay. Okay, and we're back again. Okay, fingers crossed, guys. So virtual power expression, where all the virtual velocities just have to fulfill the constraints, right? And I'm not going to write that out for now for a moment. But mind you, this was without any extra elements. So we actually have to add power from these springs. So as an extra, I have virtual power of a spring, of let's say springs. We do multiple guys. So virtual power of the springs. And what is the virtual power of the springs? Well, I call it delta PS, and it's just the force times the elongation rate, right? So it's the spring force times the elongation rate of all the springs. So the springs is 1 until a number of springs. And that we then incorporate in our equation. So we just add this guy to this guy, so we get again a delta P star, right? And I have this stuff, Mij, x double dot j, delta x dot I, plus I have this guy Fs, plus delta. And again, that should be 0 for all these virtual velocities which fulfill the constraints. Next step is of course obvious, adding these constraints, but now let's focus first on this part. We see here a variation in the coordinates, but here we see a variation in the length of the springs. And we have to write everything of course in terms of the variation of these coordinates. So we have to express this into coordinate stuff. So the big question is, what is delta dot L? What is that for that spring? Well, let's write down what is the length of the spring in our case, and that was defined as the current length times the zero length. And in our very specific case, that's now going to be the square root of xd minus xe squared plus yd minus ye squared minus L0. But what are these positions? Of course, these positions are functions of the coordinates of the system. Or in other words, I can, this position xd, which was at the top, was 0, and the yd, oh no, that was not at the top, that was the e, right? Let's go back. Oh, back. So the xe, which was at the top, was 0, and the ye was L over 2, right? But now the position of d, which was on body 1, we just have to use the coordinates of body 1. We say, oh yeah, that's the position of body 1 plus the distance. So now we have to measure from here to here. Oh, don't do that. From here to here. And that distance is this minus 1/2. So 2/3. Did it stop again? Oh no. Why is my life so miserable? somebody keeping score of this? So this was the third time, I guess. Because it also happened at the time. Yeah. Escape, that doesn't work. Yeah. Okay, where were we? This distance, so that's 2/3 minus 1/2, and then you have to make a 6th out of that, so that's 4/6 minus 3/6, 1/6. So that's plus L/6 times the cosine of phi1, and this is y1 plus L/6 times the sine of phi. Anyway, the statement I like to make is that in general, this delta L can be written as a function of the coordinates. It's just a function of the coordinates, right? Nothing, and some constants, of course. And meaning that in general, these springs, we can, if we want to know what the speed is of these springs, the time derivative, oh, well, that's easy. Then we differentiate these delta L first to the coordinates, and then we differentiate the coordinates with respect to speed. And we have a very nice shorthand notation for that. That was with the comma, delta S comma I times x dot I. So now we know if we have a spring, how does this length change when the coordinates of this body change? And that's what we were seeking. So now we have the delta L dot S is this Jacobian, delta L S comma I times delta x. Of course, in general, this is a length change. If we have a rotary motor, it's a rotational change. Actually, you could look upon this thing again as sort of a constraint type of thing, some expression in the coordinates. So I'm tempted actually to write also a C for that. So I say, every elongation as a function of the xi's I can express as some function s of xi. Why not? I generalize the whole case. And by generalizing the whole case, then I can more easily put it into my equation, because then the delta L is the SCSI, and we'll use the C all over the place. Okay, let's go back in a sec. Let's go back to my virtual power. That was the problem I had. I had my forces, I had my mass term, I had my virtual velocities here, and then I had this Fs delta dot ls virtual, right? But now we are able to write that as in terms of our virtual velocities. So we can write, oh yeah, that's my Fi minus Mij x double dot j. These are these virtual velocities plus the Fs remains the same, of course. That's just what the spring force is at that moment. And now we have this Jacobian delta Si times delta dot x. And now everything is in terms of our virtual velocities. Of course, this should hold for all our virtual velocities for which the constraints should apply. So I have to actually add my constraints, add my ck xi constraints. And how do I do that? Well, again, we make maybe a delta p triple star. I copy this. I copy this part. Duplicate, and now we put that here. So that is the first part. That's identical to this guy with the Jacobian. But now I'm going to add, of course, my constraints in with the Lagrangian multiplier plus lambda k ck comma I delta dot I. And now I can say, oh, this should hold for all virtual velocities as long as they're not all zero. So what did I do? I have my original one. I added my constraints via the Lagrange multiplier, and I added these active and passive elements. And since it now must hold for arbitrary, as long as they're not zero, I get in total I equations. So my I equations of motion are now, of course, my Fi minus Mij x double dot j, and then I have a plus here, plus this delta L s comma I, times my Fs plus my Ck comma I, my lambda k, equals 0. And these are just equations of motion. Now let's write down what the unknowns are.
Sir,
Yeah,
I have a question.
sure.
Why is compared to last week the constraints, why we add them and last week we subtract them?
Can you repeat why?
Like this week in the line above, like delta p star star, you add the constraint term, while as compared to last week we subtract them.
Oh, I always say, as you like it. It's just a definition. That's the whole thing about the homework, to interpret what the Lagrange multiplier is. Probably now, when I change this sign here, the interpretation of the Lagrange multiplier will make that the interpretation will change sign. So we can pick any sign. Yeah, it's okay. We do the different sign. So here I don't know what I did in the book. Plus or minus, I don't know. Anyway.
How do you know which way the Lagrange multiplier works?
That's in the book and that's in the homework, and if there's time I again will come back to it, because I got some questions on the WhatsApp on that. There's a problem in the book on that, there's an example in the book on that, and there's more in the book on that. Read the book. Okay, equation of motion. Now it's good to know, I mean, we now have so many variables, what is known and what is unknown, right? Well, all these matrices are known quantities, these are Jacobians which you can evaluate in the state, but what are the unknown vectors and what are the known vectors? So the forces on the right, the forces are known quantities, right? The mass matrix is a known thing. The accelerations we don't know, that we have to calculate. The Jacobian of these spring things, the Jacobian, put in the numbers, calculate. You have numbers. The spring forces, do we know them or are they unknown? I hear blah, 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 blah. Let's do hands. Those who say they're unknown. One little hand. Those who say they are known. A lot of hands. Okay, they're known because given the state of we can calculate what is the elongation, or we put it in the equation and we calculate the spring force. So it's a known quantity, depends on the state. So that's all known, this is known. And of course the Lagrange multiplier are unknown. So those are the unknown quantities. Of course I have to also supply, to get my whole system, I have my the constraints on the acceleration, right? Which was Ck I x double dot I plus Ck Lm x dot L x dot M is 0. And then this together with this, I now can form my equation of motion, right? And I put all the unknown part on the left side and all the known part on the right hand side. So the unknown part is still the acceleration and the Lagrange multiplier. And now just fill in the gap. So of course we have a mass matrix here, Mij. What else? Oh yeah, we have of course for this one Cky, the Jacobian. So this one is covered. This one is covered. Oh yeah, then I put my forces on the right hand side, Fi. Oh, and now I still have this term, but as you see, everything is a known quantity. So we just put it on the right hand side. So plus delta L s comma I Fs. And then of course we put in the constraints, so that is CKJ. Although you see an I here, I have already a J, so I have to repeat a J here. I mean, it's a dead index. You can, a summation index, you can use anything. You can use I, J, K, fietsbel, blauwe trui, pen, whatever. It helps to use single letters, but here we have zeros, and then on the right hand side we have this convective term KLM, x dot L, x dot M. Okay. Now let's reflect on this result. So we started with some multi-body system where we had some element, a spring, attached to the body. And the spring had some spring force, and we wanted to incorporate that system in our multi-body system. Now, what happened via this delta L S, I, these forces are automatically transferred to this body in terms of a Fy, an Fx, and some torque. M1, it's all body 1. I finish the sentence and then I come to you. So we have a complex system with a spring force, but then the Jacobian of our spring transforms this force into forces at the center of mass. Exactly like with the Lagrangian multiplier. Only this is now a known quantity. Yeah, question?
Yeah, the forces in the matrix vector notation, on the right side there is a force, a power present, so distance delta Ls times the force in the string.
Is that a power?
That's power.
No.
Distance times force.
Is a Jacobian of a length, is that so if you differentiate the length with respect to a coordinate, what are the units? Nothing. Nothing, Mr. Foti. I know nothing. Nothing. I know nothing. I'm from Barcelona, right? Nothing. Radians or nothing. Other question?
Have you lost the dot by the delta L?
I haven't lost the dot here. This is a Jacobian. It's a S, I.
Oh, is it? Yeah.
Yeah. I haven't lost the dot. Okay, so this is a very nice instrument. Again, we need not make multi-body, we need not make free body diagrams, but we just, if we formulate our elongation of the spring or the differential in the speed in the motor in terms of our coordinates of the bodies, then we're in business. Then just automatically the differentiation will take care of this transformation of the force to the center of mass. Now, I had a specific example, and let's look at the numbers which end with that, go with that specific example, and that is this spring here. If I now look at this delta L S, I, this Jacobian, this is not a nice comma I, then how does it look like? Well, it's in our case, because it's body 1, we only have a differentiation with respect to body 1. So I have the delta L with respect to x, the delta x1, the delta L with y1, and the delta L with respect to phi 1. Those are all the non-zero terms which we have in the Jacobian. And what are they? If I calculate them, and trust me, I'm a doctor, this is right, which I write down. In this configuration, you get these numbers for this Jacobian. 3 over 5 minus 4 over 5 minus 3 over 5 and minus 1 over 10L. I mean, please check my results, but this is what you get. If you differentiate it with respect to x, y, and phi, and you fill in the numbers of this configuration. Maybe it's good if we put dimensions here. This was L over 6, right? And this distance and this distance, this was 1/2, and this was 2/3. Meaning, if I look at this, that means that eventually this times Fs has to be a force in the x direction, a force in the y, and a moment about one. I mean, that's what I always argue. That's the way how the force should be transformed. So apparently, the horizontal component of this force is 4/5, the vertical one is 3/5, and the torque is apparently the arm, this arm distance is apparently 1/10L. And you can check that, that's absolutely true. I mean, this triangle, 1/2 and 2/3, is a 3-4-5 triangle. And that this is really decomposed in 4 and 3. And this length, this perpendicular length is really 1/10. Check it. And isn't that beautiful? You don't have to do the free body diagram, you don't have to do the geometry. You just write down the constraint, differentiate, and you're in business. And of course you need coffee.
Sorry, ik had nog een vraag over het
Tuurlijk.
huiswerk.
Ja, huiswerk.
Waar ik...
Oh ja, ik moet even wat stoppen. De recording, want dan hebben we twee recordings, dat is mooi. Zeggen we stop de recording, stop.